There's two dimensions here, and inside this, two-dimensional thing, there's a vector field. Okay, it's a force field of some kind. It could be an electric force pushing on a charged particle. It could be gravitational force pulling on something. It could be whatever, but there's some sort of vector field going on here. So there's arrows, all over the place, and they're all pointing in different directions, a little bit different, magnitudes. They're not all pointed the same way. They're just kind of generally pointed that way, but they're not all pointed the same exact way. Now, what if I have this particle that comes into play here? This particle comes in and begins to interact with this force. Okay, so this particle comes maybe something like this, and it kind of just makes its way through the field like that. Okay, so this is a path C that the particle travels. Okay, and what I really want to find out is what is the work done on this particle by this force field here. So the particle comes in, but it doesn't come in a straight line. This is an electric force or a magnetic force or something that acts on the particle, and I want to know how much work is done on the particle. Okay, so what you can do is really exactly the same thing that we did in the last section. You can define a vector that goes up. The tip of it will then trace this path as this particle goes. So we're going to use a parametric equation to describe the path just like we did before. But now instead of a function we're integrating over, it's a vector field, and so it's a little bit different. If we're wanting to find the work done on this particle by this force field, okay, what you're really going to do is you integrate over the path C, and instead of force dotted with distance, it's F dotted with dr, and you integrate that. Okay, so remember, work is force times distance. In high school physics, work is force dotted with distance in freshman physics in college, and the real deal, this is really kind of a generalization of even that. Instead of force dotted with distance, it's the integral along the path it's taken, force dotted with dr. So this integration here ends up becoming force dotted with distance in freshman physics because all those paths are straight lines. The paths aren't complicated at all. They're just, they're this way, and you push it with a certain amount of force, maybe at an angle or whatever, but basically you're dotting them together. Here, at every little point dr, really what you're doing is you're taking that force and you're dotting it with every little dr, but you're adding up all of that along this curved path. That's what you're doing. You're integrating over every little bitty dot product, F dotted with dr, as you go along this path, but you're adding them all up. That's the work done by that force on that particle. Okay, so how do we do this? We need to define what we're going to do is we're going to define r of t, which is a vector, and it's going to be exactly the same as it was before. It describes the path. Okay, that's going to be very important. And then when it's all said and done, once we define the parametric version of this path, exactly as we've done before, what is the equation going to be for this line integral? It's a little bit different because this is a vector field, and this is actually a dot product. This is a vector dotted with dr. There's something very important I left off of here. Dr is a little bitty vector. Dr, because you're dotting these things together. It's just exactly what I was telling you. You're dotting individually these little bitty things up, and then you add them all up. Okay, so how do we do this? Okay, let me switch colors a little bit. What we will say is that the path integral along C of F dotted with dr, which is just simply nothing more than taking the force dotted with the infinitesimal little bitty distance and then adding them all up along the path C. That's all that's doing. Is the same thing as the integral from a to b. Don't forget this parametric equation is defined in terms of time from a to b, just like in the last section. Okay, we take our vector, okay, and instead of all the x, y's, and z's here, we plug in the x of t's, the y of t's, and the z of t's, okay? And if this looks foreign to you, you really need to go back to the last section and you'll see what these are all equal to. Okay, and then you dot it with dr dt. There's no norm here like there was in the last section. That's a slight difference. And then you multiply by dt. This is really just a conversion factor. It allows us to take our parametric equation that we have and use it to integrate along dt. And that's what we're doing. We're transforming this integral to be an integral along dr, which is the little radius vector along the path, to an integral along dt, because it's more convenient to work in parametric equations when you're doing these things. So it's very simple. You're given a path. This path has x, y, and z components, x of t, y of t, z of t for each direction. Okay, we take the derivative of this thing and we dot it with the force field that we're interested in, and then we actually do the integration. So it's not that big of a deal, and it's not that big of a difference. The only difference between this and the last thing is here's a dot product, because this is a vector dotted with a vector that I've taken the derivative of, and there's no norm around this. And the details of those derivations I just chose not to put in the course, because you could explain it all, but you know, at the end of the day, I mean, the books are really better at some things. I mean, my goal is to really show you how to use the stuff. I mean, we could spend 20 minutes talking about maybe why and deriving all that, but you're not going to get that much more insight out of knowing that little fact, okay? But that's the way it is. So one more thing I want to tell you, and then we'll start working some problems, okay? If you have a path, okay, you're integrating over dot dr. Okay, now let's say for whatever reason you integrate along a path C, but let's say you go in the other direction along the same path. A lot of times you write that with a negative C down here. So if this were A to B, then I would integrate B to A. That's what that means. If you do that, it's exactly the same thing as putting a negative sign in along the original path. Okay, just look at that and make sure you understand it. What it's saying is that if you reverse the path, it's exactly the same thing as integrating the original path and then sticking a negative sign in front. You go integrate from here up to here or here down to here. They're both related by this. Basically, they're both related by a negative sign. That's really all that's going on here, okay? So I want to go ahead and work some problems and hopefully do a good job of making it all clear for you. The vector field that we're going to start out with, okay, is z in the I direction minus y in the j direction minus x in the k direction. Okay, that's the vector field. That's the vector field that's permeating space, and now I'm gonna have something come in on a path and interact with it, and I'm going to integrate over the path. Okay, the path is given by r sub t, which is a vector of 5 in the I direction minus sine of t in the j direction minus cosine of t in the k direction. So for every direction, I've got a function of t, okay, and it's parameterized from t is 0 to pi over 4. The parametric equation is defined in terms of t, 0 to pi over 4. So when you plug 0 to pi over 4 in for this, this describes the path, which is the tip of this vector r, okay? A couple of things I just want to point out that we're going to use here in a few minutes. This thing that's in front of the I is what is called x of t. You'll see that in the books. This is called y of t, and this is called z of t. Okay, so that's what we're going to use down below here in a minute. Okay, now the next thing you're going to need is you're going to need to know from down here, you're going to need to know the derivative of r. So let's go ahead and calculate that, and then we'll actually do the line integral. Okay, dr dt. How do you do a derivative like this? You just take the derivative of every term. Derivative of 5 is 0, so there's no I component at all. The derivative of sine over here is cosine of t in the j direction. And the derivative of cosine is negative sine. Negative times negative gives me a positive sine of t in the k direction. This is the derivative dr dt. Okay? So what I need to do next is actually write down the actual line integral. Okay? It's going to be integral from a to b. Okay? And what it's going to be is it's going to be this function, or this vector field, I should say, with x of t plugged in, y of t plugged in, and z of t plugged in. This is just converting it to being a function of time. And I'm going to multiply by dr dt, and then I'm going to, of course, integrate over dt, because that's what I'm doing. Okay? So I know the vector field up here, so let's go ahead and start doing this. From a to b is from 0 to pi over 4. 0 to pi over 4. The vector field's given to me up here. Now I need to use my functions to plug in so I can convert it to a function of time. So what I'm going to have up here, z in the I direction, z is given by this, so it's going to be negative cosine of t in the I direction. Okay, z, this is z of t right here, so I put that in, minus y, okay, but y is given by negative sine there, so it's going to be plus sine of t in the j direction. And then you have the x here given by 5, so it's going to be negative 5 in the k direction. All I did was I took my function and I plugged in the parametric form x, y, and z, and that way it's all in the function of time. I'm going to dot this with dr dt, which I just calculated here, which is negative cosine of t plus sine, negative cosine of t in the j direction, plus sine of t in the k direction, and it's going to be dt. Okay, so now I have a vector dotted with another vector, so I need to actually do that dot product there and then actually do the integration. So 0 to pi over 4, okay, I dotted with I, there's no I over here, so that doesn't contribute. J times j, I'm going to have this, so I'm going to have negative sine t times cosine of t. The j's here. And then for the k's, I'm going to have negative 5 sine of t dt. So what I actually end up at the end of the day, negative sine cosine minus 5 sine t dt. And this is an integral over t, and I have t's everywhere, and I have 0 to pi over 4. So really, this is now finally reduced to doing a regular old plain Jane integral. Okay, a regular old plain Jane integral. Well, I know how to integrate this. I know what the integral of sine is, so I can do that, no problem. I know that I want to integrate this, okay, and I'm going to use substitution to do that. So let's do this one first, okay. Let's do this integral first, okay. And what I'm going to say is I'm going to say u is equal to sine of t, okay, so that du dt is equal to derivative of sine is cosine of t, okay? And what I'm going to have over here then is then dt is equal to 1 over cosine t du. Okay, so that's my doing my substitution. This I can readily integrate without a problem. So what I'm going to do here is this integral is going to be negative sine, which is u now, u times cosine of t times dt, which is going to be 1 over cosine t du, okay? So really I'm just working on this integral first, okay? So what I've done is the cosine cancels, okay? The cosine cancels, and integration of u is going to be pretty simple. That's going to be negative 1/2 u squared. This integral is from 0 to pi over 4, so it's going to be 0 to pi over 4, but I can't plug it in yet because it's all in terms of u. So let me plug in what I know for u. U was defined up here to be sine, so it's negative 1/2 sine squared of t from 0 to pi over 4. Okay? So what does this come out to be? I'm going to have negative 1/2, and on the inside I'm going to have sine squared pi over 4 minus sine squared of 0. Okay? So on the inside I'm going to have negative 1/2. Sine of pi over 4 is square root of 2 over 2. Square root of 2 over 2 squared. Okay, that's what that is. Sine of 0 is 0, so that doesn't even contribute. So then over here, what I'm going to have over here is I'm going to have negative 1/2 times, here I'm going to have 2, square root of 2, square root of 2. 2 squared is 4. Okay, the 2's are going to cancel, and so what I'm going to have is negative 1/4 down here, negative 1/4. Okay, that's what I'm going to have here. And then this integral over here Let's do it in a different color. So yeah, this was all dealing with this integral. Now let's work on this integral right here, right over there. The integral of sine, what I'm going to have is negative 5. Negative 5. Integral of sine is negative cosine of t from the same limits of integration, 0 to pi over 4. Okay? So what I'm going to effectively have is negative times negative is positive, so 5 cosine t from 0 to pi over 4. Okay? So I'm going to have 5, and on the inside, cosine of pi over 4 minus cosine of 0. Okay? And so this is going to be 5 on the inside. Cosine of pi over 4 is square root of 2 over 2 minus cosine of 0 is 1. Okay? Cosine of 0 is 1. So let's go ahead and just distribute it all in here. And so what I'm going to have is 5 times the square root of 2 over 2 minus 5 times 1 gives me the 5. So let's not forget where I'm at here. I solved this integral and I got negative 1/4. I solved this one, I got over here. So the final answer, okay, the final answer is going to be negative 1/4, okay, plus 5 square root of 2 over 2 minus 5, okay? Minus 5. Now let me ask you this, how do I continue solving this? I want to add these two things together, these two numbers. So what I'm going to do is multiply this number 5 here, I'm going to multiply this 5 by 4 over 4. So I'm multiplying by 1. The only reason I'm even doing that is because I want to get a common denominator. So what I'm going to have at the end of the day is I'm going to have 5 times the square root of 2 over 2. And then over here, I'm going to have these two things. 5 times 4 is going to give me 20. And it's going to be over 4, so it's going to be negative 20 minus the 1, so it's going to be negative 21 over 4. Okay, negative 21 over 4. 5 times the square root of 2 over 2 minus 21 over 4, and that's the answer to that line integral of a vector field. So let's go back up to the top and see what we did. Here was my vector field that I had, and here's the path that I'm integrating it over. So there's some interaction going on here, and I want to calculate basically the work done by this field on this particle, whatever it is that's traveling on this path. So whatever's in front of I is labeled x of t, and then there's y of t in front of j, z of t in front of k. Take the derivative of the path, which is given right here, simple derivative, and here's the actual line integral. Take your vector field, convert it to a function of time by using these. You take the derivative, dot it, and then you actually integrate the answer. So once you actually look and plug in the z's, the y's, and the x's, then you get this dotted with what we calculated for dr dt. You get this at the end. And then all you have to do is integrate that. We integrated this first part separately, integrated the second part separately, and added the results at the end, and get the answer 5 square root of 2 over 2 minus 21 over 4. Okay, the next problem is going to have a vector field, x, y, z, that looks like y in the I direction plus x, y in the j direction plus z cubed in the k direction. Okay, that's the vector field. Now the path that I'm traveling and I'm integrating over to find out how this vector field interacts is r with a parametric variable of time here, cosine of t in the I direction plus sine of t in the j direction plus 2t in the k direction. Okay? And this thing is, his parametric equation is valid from t on up to pi over 2. 0 to pi over 2, basically. So that traces the path as the tip of this arrow right there. Okay? And one thing that you also need to just sort of keep aware of is that this x of t is cosine of t because it's given by whatever's in front of I right here. This is just definition. Y of t is just the sine of t given by this, and z of t is just simply the 2t. That's just a definition of what comes in front of the different components of R. That's just something you write down, okay? The next thing we're going to need to do is take the derivative of r with respect to time. Derivative of cosine is negative sine of t in the I direction. Derivative of sine is cosine of t in the j direction. Derivative of this is 2 in the k direction. Okay? Now we're finally ready to construct the actual line integral. Let's go ahead and write it down. So you have the integral from a to b. You have the vector field. You plug in x of t, you plug in y of t, and you plug in z of t, and that's just to convert the whole thing to a function of time. And you dot that with dr dt, okay? You dot that with dr dt, which we calculated right above, and then you integrate the whole thing over dt, okay? So from a to b, a is 0, b is pi to 2, pi over 2. And then when you actually look at your vector field given by this, plugging in the values of x and y and z to get your conversion going, here you have y. Y is given by sine of t. I'm going to go ahead and put some brackets around this. Sine of t, that's in the I direction, plus xy. X is cosine, y is sine, that's in the j direction. Z cubed is 2t, 2t cubed, which is going to be 8t cubed, because 2 cubed is 8, and that's in the k direction. Okay? Now this whole thing is going to be dotted with what we already found for dr dt, which is negative sine of t in the I direction, plus cosine of t in the j direction, plus 2 in the k direction. And then I'm integrating this all over dt. So it's this first thing dotted with the second thing. Let's go ahead and see what we get here. Multiplying components here, you'll have integral from 0 to pi over 2, okay? Negative sine squared of t, multiplying the I components together. Multiplying these, what you'll have is plus sine of t times cosine squared of t for that middle part right here, the j components. And then for the k components, you'll have 8 times 2 is 16t cubed, and that's all going to be dt. So everything's been converted. You have negative sine squared, sine times cosine squared, 16t cubed. Everything's in terms of t. I have everything in terms of t here, so really all you have to do is integrate all this stuff and add up the answer. So what we're going to do first is I'm going to focus on this one right here. Just the sine of t, I'm going to focus on that one first. And anytime I see a sine squared, if I don't have it memorized, I'm really just going to rewrite it with a trig identity. So what's going to happen here is, this is going to be negative integral from 0 to pi over 2. Sine squared can be written as 1/2 minus cosine of 2t over 2 dt. So that's what I'm integrating that over right there. Now, you know how to integrate the 1/2, you know how to integrate a cosine, so you can pretty much easily do that. Integration of 1/2 is just 1/2 t, okay? And the integration of this is going to be, let me keep everything straight here. There's a big fat negative sign outside of all that stuff, okay? Over here, the integral here, you're going to have the 1/2 from right here, and then this, when you integrate this cosine, you're going to have another 1/2 come out. When you integrate the cosine, this 2 is going to come out as a 1/2. Integral of cosine is sine of 2t. If you don't remember how to do this, you can just do another substitution of u is equal to 2t here, and you'll see when you take the derivative, this 2 comes out as a 1/2. So that's what you get right there. All right, and I think that's it. And you evaluate from 0 to pi over 2. Okay? 0 to pi over 2. So what you're going to actually have here, just to make it probably just a hair easier, is you're going to have negative, and then on the inside, you're going to plug in pi over 2 into here. So you're going to have 1/2 times pi over 2, okay, minus 1/4. 2 times 2 gives me the 4. And you're going to have sine of 2t, but I'm multiplying by pi over 2 here, so it's going to be sine of pi, okay, minus, over here, 0 being plugged in is going to be a 0, minus 1/4 times the sine of 0. sine of 0 coming from this right here. Okay? So on the outside, don't forget the negative on the outside. On the inside, I'm going to have pi over 4. Pi over 4. Sine of pi, I think you can convince yourself, is 0. Okay? Sine of 0 is also 0. So really the only thing that survives is the pi over 4. So what you have is negative pi over 4. Negative pi over 4. So that's just this first integral that I did. Now I need to tackle the second one and I need to tackle the third one. So let's go ahead and tackle the integration of the sine times cosine squared over here. When you integrate the sine times cosine squared dt, okay, and you're integrating it from 0 to pi over 2 just like everything else, okay, you really just need to use substitution there, okay. The reason is if you take u is equal to cosine, you take the derivative, you're going to get a sine back, it's going to cancel. So u is equal to cosine t du dt is equal to derivative of cosine's negative sine t, and then dt is going to be equal to negative 1 over sine t du. Okay? So you can go ahead and integrate this now. Integrate 0 pi over 2 sine of t times cosine, whoops, we set u is equal to cosine, so it's going to be u squared times negative 1 over sine t dt. Okay? And obviously we did that because we wanted these signs to cancel away. So what we're going to have is negative coming out. What's the integral of u squared? It's 1/3 u to the third evaluated from 0 to pi by 2. But we know that u is equal to cosine of theta, so it's negative 1/3 cosine cubed of t, 0 to pi over 2. Okay, 0 to pi over 2. And so what I'm going to have is negative 1/3, and on the inside, evaluating this, cosine pi over 2 cubed minus cosine of 0 cubed. Okay? And I think you can convince yourself cosine pi over 2 is going to give me 0. And this is 1. So really, this is 0, this is 1. So you have a negative 1 on the inside. Negative times positive should give me a positive 1/3. Should give me a positive 1/3. And that's the right answer. So coming back here just to see where we ended up. The integral of this gave me the negative pi over 4. The integral of this gave me the 1/3. I still have to integrate this. So let's do that over here. The integral of 16 t cubed dt from 0 to pi over 2. That's a simple polynomial integral, so you're going to have 16 over 4t to the 4 from 0 to pi over 2. So that's just going to be 4t to the 4, 0 pi over 2. So that's going to be 4 pi over 2 to the 4th power minus, plugging in 0, you're just going to have 0. So what you're going to have is 4 pi to the 4th power over 16. And so what you're going to have here is pi to the 4th over 4, just reducing those things down here. So we have 3 answers for the 3 different integrals here, and so adding it all up, what we'll get from this contribution is the negative pi over 4, negative pi over 4, plus the 1/3 from here, plus the pi to the 4 over 4 coming from there. So it's one of those things where you had to do 3 separate integrals in the end to actually get the answer. So let's review where we came from. We started with a vector field up here, a path that we were integrating over, and here's the time period we're integrating over. We just labeled what goes in front of I, j, and k as x of t, y of t, and z of t, and we took the derivative of the path because that's what the formula says we need to do to calculate this. The line integrals from a to b, here's the vector field, and here's the derivative of the path, and we plug in the next step what you know of the path and the dependencies of the path in x, y, and z and turn into your vector field. You dot it with dr dt, which we calculated right here, and when you actually multiply components and collect them all, you get this. And this is just an integral in t. you're going to end up having to do 3 separate integrals. So I did this integral here. This other integral was done over here with substitution, and this integral was done way over here. And so you add them all together and you get negative pi over 4 plus pi to the 4th power over 4 plus 1/3. So in this section, we've tackled the topic of line integrals and vector fields. Okay, it's very similar to what we were doing before when you were just doing the regular line integrals with a function. It's just that this one's a little bit more geared to the problems with vector fields that pop up in real life. So one example of that would be work. Okay, when you work, as we used to learn, work is force dotted with distance, but it's really the integral along the path of force dotted with dr. So you're doing a lot of these little force dotted with distance things, and you're adding them all up, and that's what the total work's equal to. And the path can be any path at all. It doesn't have to be a straight line. So the vector field is given in terms of whatever force field you have around. Could be gravity, could be something else, electrostatic. Okay, and the path is given by that parametric equation. Follow the rules here and we calculate the work done. Another good example of when you're doing these things, these line integrals are going to be in electromagnetism. You might want to integrate the magnetic field, the actual magnetic field. You may want to integrate that vector field along a certain path, and that might mean something in the problem that you're talking about, and frequently it does. So it's not that big of a deal. You just take the derivative of your path, the vector path that you've laid out, r, put it in the formula here with transforming your vector field to function of time and integrate over dt. That's how you integrate line integrals in vector fields.
Learn anything at mathandscience.com.